So this video is going to explain how we balance nuclear reaction equations. And nuclear reactions differ from chemical reactions in many ways, including the way we balance their respective equations. So one way that we would differentiate them is that in a nuclear reaction we actually have not only the element symbol but also the atomic mass and the atomic number listed in the actual equation itself. Therefore, not only are we balancing the reactants and products, but we're really balancing the atomic mass and the atomic numbers. So in a chemical reaction, we're taught that matter can neither be created nor destroyed, which is still the same in a nuclear reaction. But what we're really conserving is the atomic mass and the atomic number in a nuclear equation. We're not necessarily concerned with conserving the element, because if the atomic number down here changes, that means the proton number also changes, and that means that our element changes. So the element's identity can actually be changed. We can transform one element into another. So we're not going to be looking for element X on the reactants and element X on the product side. We're not going to be able to balance the same type of atom because most likely the same atom will not exist on both sides. But rather what we're going to attempt to balance is the atomic mass and the atomic number. Now the atomic mass, recall, is the sum of the protons and the neutrons. And the atomic number is your number of protons. So that is what we're going to balance, these two different entities on the reactant and product sides, not necessarily the element. The second main difference that you will find in a nuclear reaction is that not only do we have elements, but we also have nuclear particles that we will be using as reactants and products, because that is what is allowing this decay or transformation to occur. So we have 6 different nuclear particles listed here. We'll begin with the proton. Symbol is P. Top number is, of course, 1 because it has a mass of 1, and the atomic number down here is a +1 because protons have a +1 charge. Neutron is another nuclear particle. Symbol is N. The mass, of course, is 1, and it has no charge, so the bottom number is 0, meaning it has 0 protons or charges. The electron is also considered to be a nuclear particle. We can write this 2 different ways. We can write it as an E for electron, or we can actually call this by its nuclear name, which is a beta particle, this being the Greek letter beta, the beta symbol. So, of course, we have a mass of 0, because that's what electrons have, and a charge of -1, meaning that it's not only not neutral, but it is lacking in 1 positive charge, or it has a -1 charge. The opposite of the electron, an anti-electron, if you will, a form of antimatter, is the positron. And a positron is basically a positively charged electron, meaning it is a substance that has a mass of 0, but yet has a +1 charge. So it also uses the beta symbol or the electron E as a symbol, but it has a mass of 0 like the electron, but it has a +1 charge. We also have an alpha particle. This is one of the higher forms or intensities of radiation, and this is represented by the symbol alpha with a mass of 4 and an atomic number of 2. This is the same mass and atomic number ratio as a helium atom, so you can alternatively write the symbol for the element helium. And last of all is the gamma particle, the highest intensity here of the nuclear particles, and that has a gamma symbol with a 0 mass and a 0 charge. So these actually will either be a reactant or a product. So one thing to look for is the term decay or capture or emission. If you're asked to write the equation in its entirety, a decay means that one substance, say X, is decaying into another substance Y. Same with emission. most likely X is being transformed into Y because of, say, a gamma particle. So an emission means that this nuclear particle is being emitted or is being produced and being lost. Same with a decay. It is likely being produced and lost, and one particular element is being broken down into another. So decay and emission typically look at one substance forming into another with one of these nuclear particles being involved, most likely being in the product section of the equation, meaning it's being produced and released. If you see the term capture as an electron capture, then most likely you have your element X capturing that electron and then forming element Y. So look for the terms decay, capture, emission to determine exactly where your nuclear particle could come or should be placed. Okay, so let's take a look at a couple of examples down here, and we want to look at a few basic premise of how we want to balance our nuclear equation. So the first thing we want to do is look at the atomic number, which is the number on the bottom, and make sure that that is balanced. Once we're able to do that, we can figure out either the nuclear particle that's involved or the new element that's been formed. And from looking at the new atomic number, we can search on the periodic table and determine what the symbol for that particular element is, the new symbol. And then of course we will go to the top number, which is the atomic mass, and ensure that that is balanced. Now, one main thing to note here is when you are balancing the atomic mass, the number on the top, you definitely want to make sure that you do not just simply take the value that you see on the periodic table and write it into your equation. Remember that the number on the periodic table listed for mass is the average isotopic mass. It's not the exact mass for this particular isotope of whatever element you're forming. So it has to be specific to this particular reaction. The only way to balance the atomic number is not by looking at the periodic table, but rather adding it up and balancing it in the equation itself. The only thing we'll get from the periodic table is the element symbol from the corresponding atomic number. Atomic numbers and symbols never vary, but the atomic mass certainly does, depending on the isotope with which you are working. So let's take a look at this particular example here with polonium. So polonium here is decaying by alpha emission, which means decay, one substance decaying or breaking down into several others. That's a decomposition reaction if you think chemically, and we are emitting alpha particles because they are being produced. So if you were to be given this in written form, it would read that polonium-212, the 212 isotope, decays by alpha emission to form what element? So let's take a look. 2 is the atomic number here for the alpha particle. 2 plus what value here would give us 84? That would be 82. 82 plus 2 is 84. So we're just balancing numbers. It's as simple as addition and subtraction. Now let's look for number 82 on the periodic table. That tells me that I have lead, symbol Pb. And if I look on the periodic table, the mass for Pb listed is the average mass, hence you see in this decimal value. We don't want to use that mass. It may be the same as what we just calculate, and it may not be. If it is, it's purely coincidental. So we never want to just refer to the periodic table for the mass. It may steer you wrong. Always calculate it for yourself. So 4 mass from the alpha particle plus what other mass gives us 212? 208. 208 plus 4 is 212. So the isotope of lead that I have here is the lead-208 isotope, and that is the other product formed when polonium-212 decays by alpha emission. Simple enough. All right, let's take a look here at another decomposition. This is the 11 isotope of carbon. We're always used to seeing carbon as 12.01 on the periodic table, but this is the 11 isotope, and it is also decaying to form something. Boron number 11, mass 11, and some sort of radio nuclear particle is involved. So what nuclear particle? Carbon is decaying by what kind of emission to form this boron product? Well, let's see. What mass and what atomic number would it be? And then from there we can identify which of the nuclear particles we're dealing with. So what atomic number plus 5 makes 6? Obviously 1. What mass plus 11 makes 11? Obviously 0. So this is a positive 1 plus 1 and 5 makes 6. 0 plus 11, right? Plus 11 makes 11. So what nuclear particle is 0 plus 1? Of course, that is the positron. We can also use the symbol beta. And that is what goes here. All right, let's take a look at one more example. In this case, our nuclear particle is not a product like this alpha emission and not by this positron emission. You may have heard of positron emission or PET scans. That's what that would be. So we're not looking for alpha emission or this positron emission, but rather we're looking at our nuclear particle here being a reactant. This is a capture, and this happens to be a beta particle or an electron, so this would be an example of electron capture. So we're looking at argon-37 decaying by electron capture. So let's look. 18 is the atomic number plus a -1 means we have 17 as our atomic number. So I'm going to look for number 17 on the periodic table, and that is chlorine. Now, you would see 35.45 listed for the atomic mass of chlorine on the periodic table. Obviously, we don't use decimal numbers, number 1. And number 2, that would not be the correct mass. This is not this 35.45 or 35 or 34 isotope of chlorine. 37 plus 0 is 37. Therefore, this is the chlorine 37 isotope. If you had just picked the mass out of the periodic table, you would have gotten, of course, the wrong value for mass. So make sure that you always calculate both your atomic number and your atomic mass, and just refer to the periodic table for the symbol, as that, of course, never changes. So if argon decays by electron capture, it will form or transform into chlorine 37. So again, just make sure your top and your bottom numbers match up and are equal on both sides, and that matter is conserved in that way. And you're not looking to see if the same atom appears on both sides, because that's certainly not going to be the case on any of these. None of these have the same atom on both sides. But what we're looking to balance rather is the atomic number and the atomic mass, and identify our nuclear particles that are involved in each of these decays.